Okay, so let's begin. So in this class, we will finish this slide, okay, and then we will go to the review slide, and hopefully we can finish today, but very likely we will extend the review to Wednesday. And today we will also have the new quiz for this slide, okay. And the review slide will be very comprehensive, which means, excuse me, which means that all you need is to look at the review slides. All our questions will be some here and there in the review slide. Okay, and just do good preparation according to the review slide. You should be good, right? And our exam is on Friday, which will allow you enough days to do preparation. And so the review slide has also been shared on Canvas. If you look at the dynamic syllabus, the last item is a review slide. Okay. So the deadline for the quiz for this this PPT file will not be due before the midterm, but it's highly recommended that you finish that quiz before the exam. Okay, because that will help you in preparing for the exam. Okay, so continue with what we discussed last time. We told you that IPv4 is very limited, right? So it's only 4 billion addresses, but in the world, we already have like 7 billion people, right? Because of this reason, we are now moving to, in the process of moving to IPv6, okay? And so IPv6 actually originally designed in, 1998. It has 4 times the number of bits, right, compared to IPv4, right? Which means every person will be allowed enough address space. And the IPv6 is a group of 8 values. Each value has 4 digits, which is hex digit, okay? So which means even though there are only 4 digits here, it's actually 16-bit. And we can ignore the leading zeros, only the last zero for here. We can have 42 only here, right? And they are separated by column. And because we typically don't use all these numbers, right? So some starting from the left-hand side for the network address, some from the right-hand side for the host address, okay? And we will have a bunch of zeros in the middle. And if that is the case, we can use two columns, right? To mean that there's a consecutive bunch of zeros in the middle. Okay. And IPv6, the local host is just a 1, the last, the last bit is 1, the other side. And here's the IPv6 header. So we discussed that before, so we will just move quickly. Okay, version 6, okay? And this is quality of service, okay? Yeah, for QoS, this is groups packed into floats. And so there's a datagram length, which includes also the data payload. This is just a header here, okay? And the next header is really the protocol, right? So like TCP UDP, encapsulated in this IP datagram, okay? And the hop limit is like TTL, right? You can use it for trace route, right? You can use it for avoid looping also. And the difference from IPv4 header as follows. So now header length is gone, right? We roll to the next header, okay? Just we'll go to here, right? And so identifier flags offset, which originally is used for fragmentation, is gone, okay? Because IPv6 no longer allows you to fragment. Okay, you need to probe for the minimum MTU on your route first, okay, and then send packets, no larger than the minimum bottleneck MTU, okay, pass MTU discovery. And it also reflects changing internet priorities, right? Because now, maybe in the future, all IPv6 backbone routers will be almost the same. So there's not much need for this complex stuff like fragmentation. Maybe the MTU is the same, right? Instead, doing those operations like fragmentation is costly. Any questions? I see some students. If not, I will mute or temporarily. Okay, if you have questions, feel free to ask. Yeah, so instead, the efficiency is the most important, right? So the routing costs, or if you do fragmentation, it would be slower, and a lot of circuits, hardware to do that, right? So we want to keep things simple, right? So IPv6, if you look at the header, it's way simpler, right? Just 2 rows, and the IP address cannot be saved, okay? And it's larger, 4 times larger actually, right? And the hosts are expected to, let me see. And there's no security vulnerability, right? Because previously, if you have IP fragment, you can do attacking. Right? You can embed and replace a fragment, or you just hold the fragment never arrive and memory attack, etc. Okay, now we don't have those concerns. So there are some performance improvement, right? So because of the simplification, okay. Firstly, there's no checksum to verify, okay, because we totally remove the checksum field, okay. There's no need for routers to handle fragmentation, okay, because there's no fragmentation now, okay. So routers can be much simpler and just forward, okay, and look up the routing table and forward, storage and forward, okay. So the routing table design is actually also simple, as we discussed last time. This is all the review, okay? Because we now have 128-bit, right? So the first 64-bit can be used for your network. The last 64-bit for your host ID within the network. And your host ID can be random, because the probability that if you randomly sample host ID, the probability that 2 host ID are exactly the same is super low, okay? So just a randomly assigned ID, that's fine, okay? And so this also improves the, network ID has to be detected by so-called neighbor discovery protocol, right? Network ID uniquely define your network, which is the first 64-bit. But then in that network, you have so many 2 to the power of 64 addresses, okay? Which is even more than IP address right now, IPv4, right? Only 32 bits, right? 2 to the 64 is more than all the IP addresses right now, by 2 to the power of 32 times, okay? Which is 4 billion times the current IP address. So this is really large. You can just randomly sample host ID for you to use. Let me see. So also additional IPv6 features. The first is called source routing. Okay, the host specifies the route it want to packet to take. Basically, I want to go this path. I don't want to go that path. Right? Maybe that path is a little bit dangerous. There will be attackers. Okay, the adversarial attackers. Okay, and you can also have mobile IPs, which means that you can take IP addresses to other networks. If you remember, your network segment, right, determines your location, right? We do analogy using the phone number, okay? But you can actually bring your your IP address with a network field to another location, right? So there will be some handover stuff, right? So to guarantee this is properly done, okay? So you can use a source routing to direct packets, okay? Right. And so that's why, things will be properly handled, which means you can have a mobile IP, which is the same IP address, but you can go to different locations. And there are also some privacy extensions, like let's say because now our host domain is so large, 2 to the power of 64, you can randomly generate a host ID for yourself to use, okay? And this makes it difficult to associate one IP to a host, right? So, you can be any ID, okay? So this helps you to be secure. But if you are a malicious user, right, you're attacking other people, okay, then it's also difficult to find you, right? And that's also called the jumbograms, right? And this is, IP is a datagram, right? Jumbogram is a super large datagram, okay? Now IPv6 can support 4 GB. B is a bit, by the way, okay? 4 GB datagrams, okay? It's a 500 million, basically, okay? If you look at a byte. But it's super large datagram if you look at the datagram size. And so is it easy? Because right now we have IPv4, right? So all we do right now is to make all devices, like you buy a router, it's IPv6 compatible, but still it should operate IPv4. Okay. Well, is there a challenge here? The answer is really yes, right? Because we see that you can have in the physical layer and in the data link layer, you can have very different technologies. Okay. And above IP, you can have TCP, UDP, and then you have HTTP, all kind of protocols. But in the middle layer, which is the IP layer, you only have the IPv4, right? Okay. And switch to IPv6 is a whole internet upgrade, which means everyone, including your host, your tablet, okay, your phone, right, and even the backbone internet, right? The internet service providers, their routers, all need to be upgraded. Maybe they don't want to upgrade, right? So they are running fine. Okay, the upgrade takes money. Okay, so this is a very difficult process. All routers, all hosts should be upgraded. Okay, and all protocols up level, okay, should be upgraded, right? So like ICMP, this is a control message, okay, should go for version 6 instead of version 4, right? DHCP is a protocol we will see later for you to, assign IP address to laptops, right? So, when you go to UAB Secure, for example, right, the Wi-Fi, it actually runs the DHCP to assign the IP whenever you join, okay? Different times you may get a different IP. Okay, they will go get an IP that is not used outside to you when you connect. And there's also a DNS, right? So domain name service. Okay, this also need to be v6. Okay, the only service is in the application layer, not in the transport. Okay. And by June 2012, only 0.2% of the traffic is IPv6. Right now it's much higher, but again, it's not that high. Okay, you can see like in 2019, it's just 25%. Okay, so this will be a long-term process because it's a bottleneck layer. Right? Everyone need to upgrade this. So in order to smoothly transition from IPv4 to IPv6, right? It's like now we need to handle both IPv4 and IPv6 packages, technologies, okay, smoothly until like upon some certain point, right? So majority of people, right, are using IPv6 or compatible with IPv6 with their devices. So you can pull the trigger. Hey, I will no longer support IPv4. Okay, this is like Python 2, right? So these days, right? We are forced to use Python 3 because Python 2 is automated. Okay, but that process will be much longer. Okay. So most internet network edges right now are IPv6 ready, which means when you buy a new router, tablet, or even you buy a new computer, they all support the network interface card all support IPv6. Okay. And what's difficult is the internet core, right? It's a service provider. Okay, you cannot force them to upgrade. Okay, and gradually they will upgrade finally, right? But again, it's their own choice. Maybe they invest millions or even billions in the infrastructure. If you wanted them to totally replace, it takes some time, okay, if they don't see much incentive. So the edges are mainly already IPv6 ready. Oftentimes it's the core internet, right? So the routers in the middle that helps you is IPv4, okay? So the problem that, if you directly send IPv6 packet from, let's say, the home network to the business network here, right? It's not gonna work because, this is a newer version, right? So the core internet is looking at the older version, okay? So it means that you need to do more as a edge devices, okay? You cannot ask the core devices to do more. Core devices only know up to version 4, okay? If you want a version 6, you need to do something to make version 6 compatible with version 4 so that the core internet can use version 4 technology to do that. Right. So how to do this? Right. So we need a so-called transition technology. Okay. So what is the transition technology? Right. So how do you route IPv6 packets over a IPv4 internet? Which means the internet is still IPv4, but your packet is IPv6. Right. So there are many transition technologies. Right. So usually you can use so-called tunnels, right, to encapsulate and route IPv6 packets over the IPv4 internet. Right. So basically you have a shell, which is an IPv4 shell, right? So which the router will read, okay? But at the end, at the edge, you can take out the shell, right? Take the meat out, right? So which is IPv6. Okay, so this is a just an intuitive idea. Right? So we have many different technologies to do that, right? So one implementation is 624, right? So it's quite intuitive in the name, right? So from IPv6 to around 4, okay? And there's another technique, IPv6 rapid development, okay? And the Tornado, okay? And we will look at what they are okay, in the next few slides. So what is 624, right? So, assume that you have been assigned a IPv4 address because when you connect to the internet, right? You have you get your IP address from the service provider, okay? And they will give you IPv4 address, but you want an IPv6 address, right? Because you want to have IPv6 ready technology, right? So how can you do that, right? Your ISP won't give you a IPv6 address, and you cannot just choose arbitrary IPv6 address, right? So you need to. So basically, that should be a mapping from IPv4 to IPv6. It basically says, hey, for this IPv4 address, you should use that IPv6 address. Okay. Solution is to contract a 624 address. So this is a quite unique mapping. Okay, so the first bit, you remember IPv6, the address has 8 segments. Okay, the first segment is always going to be 2002. Okay, when you see 2002, you know that it's encoded using 624, and it embeds this 32-bit IPv4 address, which is like here, illustrated here, inside a 4 times the number of bits, right? 128-bit IPv6 address. So how to do that, right? So firstly, the first segment should be 2004, 2002, like we discussed here, okay? Then the network field, remember the first 4 segments are network field, the last 4 segments are for host, right? So the next field, right? Like let's say these 2 bytes are network field, then we encode them, okay, into here, right? This is 1 byte, this is 1 byte, and each here is 16-bit, which is 2 bytes. So we can encode these to here, but we use the hex digits to represent these decimals, okay? And then we will represent the host, right? So using this, okay. So basically, you are not using all the segments. Okay, you are using 2002, and then you use one segment to encode the network. The network part of the IP addresses, and you have another 16-bit to represent the host part of the IP address. All others are 0. Okay? So this will give you something like this, right? So in that case, how does a host use 624 to send a packet to another host, right? So let's assume they are both using 624, okay, right? So they both start from 2002, and this is a network segment for here, and this is the host, and this is the next segment for here, and the host is 0 goes here, okay? So how to do that, right? So firstly, let's assume you have an IPv6 data graph, which means the destination that is this guy, okay? But you cannot just send this packet through the IPv4 internet, right? So what you do is you do turn, right? You wrap it into another header, and the header has the IPv4 address here, okay? So keep in mind, we have the yellow arrow here, right? Or we say orange arrow, right? So the orange arrow says that, hey, we know that mapping. So basically, I can translate the 104F to 16 and 79, okay? And I can translate 080 to 8.0, okay? And then I can easily wrap this header, IPv4 header, based on this destination. And then I pass this thing to the linter, because the IPv4 routers will understand this IPv4 address and know where to put it to. Right? It will finally arrive at the destination. Okay, but the destination only needs the IPv6 packet. Right? It can then that removes the header for IPv4. Okay. There's a question. So is a column a word? So column is not a word. Okay. Column is separator. Just So how to say this? So this, if you remember, we said that IPv4 we have this dot, right? This dot. I see a question from John, so let me just clarify in case they make confusion. Okay, so this dot is not meaning any bit. Okay, it just says we have 32 bits, but we segment them into 4 8 bits, right? So this is for IPv4. For IPv6, we do something like we have 16 bits for each segment. Okay, we have 8 such 16 bits. Okay, this column just separates those 16 bits. Okay, it's just for notational simplicity. Okay, let me see. Yeah, it's a separator. Yeah, exactly. It's help you to memorize it, right, into segments. Otherwise, if it's a long string, then you cannot not remember. But actually, you say do not occupy anything. Okay, say do not occupy anything. So yeah. So the next technology is routing from 624 to native IPv6, which means you have a native network which is IPv6 compatible. Oh, just give me 1 minute. Okay, I will be back. Sorry.
Am I going nuts or did our professor dip?
He said
He said he was coming back.
Oh,
yeah,
my bad.
I'm coming back. Sorry. Yeah.
Welcome back.
You're welcome.
He tried to take over the class, I guess.
Yeah.
Do we have a test this week?
Yes, Friday.
Oh my god.
Friday the midterm.
Okay. All right.
Yeah.
Are we gonna have like a review for that on like today or like on Wednesday?
Review will be. Let me see if we have enough time. We'll do part today. I don't think I can finish it today, so we'll also do it on Wednesday. It's okay.
Okay. All right. Thank you.
Okay. You're welcome. Right. Let's continue. All right. So next technologies. If you have part that, let's say this router, this part of the network is already supporting IPv6, right? But this part is only supporting IPv4. Okay. What will happen here? Okay. Let's look at what will happen. Okay. So here, let's assume we have an IPv6 packet, but can only route to here, right? But this router already knows it. Okay, so if you can go to this router here, then things should be fine. Okay, but how do you get to the router, right? So again, because this IPv4 internet is not supporting, okay, again, it's the same. Okay, so you compute the IPv, you compute from this destination, you get the IPv4 address. Okay, so this is the give to 624 relay routers. Okay, and then you pass through this, right? So this is 624 relay routers. A lot of ISP already have that, right? Basically, upgrade to IPv6 in some sense. Okay, But you cannot just do IPv6. It have to be 64 because that's part of the internet. That's to IPv4 only. Okay. Then you can send this packet to this router, and then you can drop that address and do here. Okay. So here, one thing that you need to pay attention is different from the previous one. Right? So you can see here, firstly, this is not this destination is not 2002. Right? This is very important because here this part is already IPv6 supported. So basically this can be any IPv6 address. It's not using 624. Okay, but this router itself is 64. So you can see the router has 2002. Okay, and the router itself, this ISP has a router address, right? So when you translate to here, you should know, hey, this router is already a 64 router. Okay, relay router. And so you need to know its address. And the only way to do that is, the ISP need to provide you this mapping. Okay, basically, if ISP provide you this mapping, then you can route it accordingly. And you then unwrap and then go to IPv6 network. And now let's consider the reverse process, right? So what if you want to go from here, the native IPv6, back to some network that only has IPv4 component. Right? So what you can do is this, right? So you can have a IPv6 packet, right? Destination, of course, because this host is using 624 technology. Okay, so you need a stand to this router, but this router, as we said, it's a 624 relay router. It will add the wrapper. Okay, and now you know the mapping, right? So their mapping is fixed. Okay, you can send to the destination, you know the mapping, and this can be added and sent to the destination. And then the destination will get the IPv6 packet. So put simply, all you need to know is that there's some transition technology, and there will be a wrapper outside with IPv4 address for you. Okay, and some, all the way go to the host. Some can already have some, 624 relay router, which means it's already one level above. Okay, and if you have this relay router, your IP address, IPv6 address, do not have to be a 624 address. You can use any address, which is nice. Okay. So there's some problems with 64, right? So there's a uniformity issue. That's not all ISP have deployed this kind of relays. Okay, this relay router, and there's also some concern with the quality of service, right? And so, there's not many such routers, so they may be overloaded, okay? And they may not be reliable. And another issue is that, the reachability issue, because currently the NAT, which is a network address translation, which means if you have a public IP address, you can share it with a lot of computers. Right? You have the internal IP, and then they will do the translating on the NAT interface, okay? Interface router. It will do the translation, network address translation, okay? And to direct to which internal computer you want to send. Right? But 624 cannot work with this. Okay? So there's possible solutions. Right? So one is the IPv6 rapid deployment, okay? And it does not do the 624 like using the 2002 address space, okay? And each ISP sets up a relay for its customers, okay? And there's also Teredo, right? So which channels IPv6 packets through UDP or IPv4 channels. Okay. The nice thing about Teredo is that you can tunnel it through the nets. Okay, unlike the 624, you cannot turn it through the net. Okay, so but it requires special relays, okay, because if you don't do this, you are basically the same as 624. And the consequence of IPv6 is that some technology is no longer practical, right? Previously, you can have an IP blacklist, which means, hey, these are malicious IP addresses, okay? If your destination is ever go to these addresses, let's say your browser give you a warning, like a red web page, hey, this is not secure, etc. Okay, but now it's not practical because IPv4 addresses the size are reasonable, right? But IPv6 you can randomly sample as an attacker or a bot, right? You can randomly sample an IP address, okay, and then do the attack. And if you are blocked, right? You are blacklisted. You change another one, okay, because you can have so many, right? So this is no longer practical. Okay, blacklist is not working with IPv6. Okay, so that's basically this slide. So our midterm will go all the way till this slide. Okay, actually this is not finishing our network path because we have not talked about how to route, right? So we are basically talking about IP address, okay, and how the datagram looks like. But then this datagram, how to put into the routers and how they route, and how to find the best route, etc. Okay, these parts are much more difficult. A lot of algorithms there. We will not go too deep in the algorithm. Right? So like Dijkstra and so the algorithms we will cover them after the midterm. Okay, in the final exam we may have some question on that. Right? So midterm is really mostly on the concepts. Okay, and next let me go through the review slide. Okay, that we shared. And again, some students asked me today, right? So actually, I sent an announcement that this Friday will be the midterm exam, and the lab will be canceled because we have some students need special accommodation, which will time to make the time. Okay, that will overlap with the lab time. We will restore our lab in the next week. Okay, this week we have no lab, and this also allows you to prepare for the midterm fully. Right? And so here is a review of the midterm questions, but let me see the time. Okay. We don't have too many time. Let's go back to the last question. Okay, so so basically these are all things that we will cover. All the questions should already be in this slide. Okay, we double checked with the TA. The TA actually helped prepare most of the slide. Okay. So let me go to a example of the IP, right? Because we have been talking about this for quite a few days, right, a few classes, okay? So this may be the closest to us before we review the earlier layers, okay? So here we can have example, something like this, right? So we can give you, again, here we are using binary strings, okay? Sorry. Okay. Right, we can tell you, hey, this is the first segment, but we are not writing decimal, but this is just the IP address, okay, for segment, right? So consider such a datagram network, right, using 32-bit host addresses, right? And we are considering a router that has 4 links. Okay, so we have a router with 0, 1, and 2, and 3, okay? And the packets are to be forwarded to the interface as follows, right? So basically, if your IP address are within this range, from this number through to this number, you go to, you will be put on this port. Okay, if you are within this range, you will be put on this port 1. Okay, if you are within this range, you will be put on port 2. And if you are outside all these ranges, that's otherwise, you will be put on port 3. Okay. Sorry. So the question something will you have a question will be something like this, right? So provide a forwarding table, right, with that has 4 entries, right? Use longest prefix matching. So this question really, like this, is really testing you the longest prefix matching concept. Okay. So let's take a look at if you have such a question, how to answer that. Firstly, look at this segment, right? So how can we handle this, right? So firstly, you should notice, okay, this is the prefix, these are the same. And moreover, so if we put this as a network segment, right, and this as a host segment, you can see the whole host segment are actually to 0, right? Because it's from 000 to 111. Okay, anything that starts from this network address will go to 0. So it's pretty simple. So if your prefix is this thing, right, and then you should go to 0, right? So the next one, if we look at the next one, it's kind of similar, right? So if you look at here, let me change the color. So you can see it's analysis the same. Okay, this is network address and any, no, sorry, this is not correct, okay, because we can continue push it. So let's go to here. You can see anything starting from here, right? Because this is from 00 to 111. So anything with this starting from this subnet address goes to you. Okay. Now let's look at the third one. The third one is quite tricky. Okay, you can, so for example, you can see this. Let me change another color. Let's change it back to red. Okay. This bit, how to say, should be this bit. Okay. This bit is already different. Okay, so and you can see this is 1001. This is 101. So this looks quite complicated to you, right? So how to handle this question, right? So there's some tricky part. Okay, so the solution is really using so-called longest prefix matching idea, right? So let's see how to handle this. Firstly, you need to keep in mind. Firstly, let's take a look at these two numbers. Okay, you know, IP segments usually don't overlap, right? So if you overlap, you use this longest prefix match. So if you look at these two addresses, first is this address, and second is this address. Right? You know, this is really +1. Okay, after +1, this is 101, +1 is 1000. Right? The other side. Okay. Right. So noticing this, actually you can do something quite interesting. Okay, so you can cut here. Okay, you can cut here. Right. So say, hey, everything started from here should go to 2. Okay, so will that cause problem? No, the answer is no. Even though, let's say, some of the address, right? So in the previous segment, okay, let's use the purple color, right? Should go to 2. Okay, right? This should go to 2. It also starts from this. Okay, it's the same as your range. But you remember, so when you go to 1, this is the longer prefix. Okay, so according to the longest prefix matching, even though it matches both this range and this range, it will go to 1. Okay, 1 will be prioritized. So it's fine. So you can say here, if it starts here, I will go to 2. Right? There's no worry of any kind. Okay. Any questions here? So you can use a shorter interface. They go to 2, but some of them will go to 1. But that's fine because 1 has a longer prefix. Okay. And finally, we have the larger than this, you will go to 3, right? So to handle this, you just notice that let me change another color. Go from here to here. Right? What's this number +1? This number +1 will be 111, 0001, and this is 0111. Right? It will be 1000. Okay? So which means the next segment will be totally using a different prefix. Okay. It's the first bit in the second byte is 1. Okay, while here all the previous one is 0. So basically, starting from where the second byte bit is 1, all these prefixes will go to 3. Okay, or larger, all the way to large, because this is smaller. These ranges are kind of consecutive. Okay, and of course you need another additional item because when you say, hey, this is 11001, right? So this goes to 3. What about a number prefix larger than this, right? That's tricky, right? So there's no item for that, right? So you need to say otherwise. Okay, for the others also go to 3. So which means you need 2 items for 3. Okay. Any question about this question? This example how you can handle this kind of question, right? This could be the most difficult kind of question we will test you. Any questions? Yeah, the next question, if you see like other questions are quite simple, right? So if you look at this, you just check the range. You can use the prefix matching, right? Because all you need is really the prefix. Once you have the routing table, it's easier to check. You just check to where necessary, and you do the longest matching, of course, right? And then you decide which port to go. And finally, we write the following table using the CIDR, right? CIDR address. This basically requires you to use a decimal, right? And use how to translate from binary to decimal. Okay, these things I will just skip. But if you are not familiar with that, do some practice of that because the exam is time. Okay. Okay, let's go back to the beginning. beginning, and let's look at all the logic points. Excuse me. Okay, so firstly, you should remember this, right? So I hate to say this may not be necessary, okay? But people need to remember this, okay? This is called the OSI, right? It's a standard 7-layer model, right? 7-layer. Of course, as long as you can remember physical, data link, and network, transport, and application, that's often 5 layers, which is enough, okay? But according to OSI, we also have the permutation session layer, okay? So because of this reason, we'll have, this is layer 1. Starting from layer 1, it's physical layer. According to our description, we are also following this order. Then 2, 3. We are now right here, right? We haven't finished the routing part. In the second half of the course, we will go to 4 and 5 and some additional advanced topics, okay? So, but you need to remember session layer and presentation. For example, session layer is 5, okay? Presentation is 6, this is 7. Okay, we might test you, okay? We might very likely test you this question. You need to know, for example, presentation layer is above session layer, right? Below application. Don't reverse these two. Okay? This will cause mark to be deducted. Okay. Even though in reality,
why did session have an X through it?
What?
Why did session have an X through it? Yeah, an X over it.
Have a what?
Well, just
Sorry.
a second ago you did.
Okay,
so you had like an X over the session part. I was just wondering why that was.
X? I don't see X here.
Or it looked like an X. It looked like an X the way you drew it.
You mean here? I don't see an X here.
Yeah, you took it off like just a second ago. You had like a bunch of stuff on there. Don't worry about it now.
Yeah, there's no X. So this is a 5. Okay, sorry.
Okay.
Yeah, so we need to number it, right? So this is layer 1. So let me see. This is layer 1. Okay, this is layer 5. Maybe you look at 5 as this is 6, this is 7. Okay, because there's 7 layers.
I don't know. Okay. All right.
Yeah.
All right. Thank you.
You're welcome. Yeah. So you need to number them, order them. Okay. So because we may ask you layer 4, then it means transport. Okay. So keep that in mind. So the physical layer, we described it, right? So if you know, it's really the hardware, right? So the coaxial cable, fiber optics, and the radio, right, for wireless. Okay, you need those things, and it's a unit in the unit of bits, right? We have the non-return to 0, these keys. Okay, and then we have the data link layer. Data link layer is really we have the packets unit, right? We call it frames. Okay, so this data framing. And we also have the MAC address control. And this is actually a very important segment for things that we will be testing, okay? And you need to know that we have so-called MAC address, which is the 48-bit, right? So, and we have Ethernet, Wi-Fi, both are in this category. Yeah, I see a question. So basically, in reality, we don't really use the presentation session layer, right? But we need to memorize them. We will test it because OSI 7-layer model, everyone should know it. Okay. And then, so we will go and review this data link layer, and then we will go to network. Okay. So in the data link layer, you need to know the concept of framing, right? So the physical layer determines how bits are encoded, and the framing layer will, consider now blocks of data, right? And so this is because we have a packet switch network. You have basically packets, right? So we're routing, and we need to know data boundaries. And we just discuss the 3 methods to do the framing. One is called byte oriented, one is bit oriented, one is clock based. Okay, we'll go really fast because there are quite a number of slides. So for byte oriented method, you need to know that we have the start and end, setting. Okay. And what if these bits, Sentinel bits, happen in the middle, right? So it should not be end, for example, right? You need to have a so-called escape, right? DLE, data link escape. So when we talk about DLE, you should not be strapped, right? So DLE means data link escape, okay? So if we have a question and say, hey, something from DLE, you need to know what it is, Okay, it's data link escape. Just escape the data item here for byte oriented method, right? And another scheme without a DLE is just to say, hey, how many bytes you have, right? And then you just count so many bytes. Okay? You know the end is after 132 bytes. And the second scheme is called a bit-oriented scheme, right? So it's bit stuffing, okay? And so in this scheme, we have, also we have those sentinels, right? These bits, right? And in this case, this bit will have 6 ones, right? So as long as you can guarantee that in the middle of the data you don't have 6 consecutive ones, then that's fine. So whenever after 5 ones, you will add a 0. Okay? And there are some additional details that you can look at. And there's also clock-based method, right? Like the sonnet method. This is really for optical links. Okay, so because the speed is so fast, so you have much larger bandwidth in rows. And so basically, there's some physical layer details like non-return to 0, and so there's a special XOR, right? So the exclusive OR operation to avoid long sequence of 0 points. Okay, and then we have the error correction, right? Error detection correction. Right? So the parity bits. Right? Parity bits means if you have 7-bit ASCII, characters. And for you want to encode it into 1 byte, right? So you need to add another bit, and you want to make sure there are an even number of ones. Right? Here you have 1, 1, 1, 1, 4 ones. Okay, but you cannot have an odd number of ones. So basically, we'll add those bits to make sure the whole byte only have even number of ones. So this is called parity bit. And we also have this can detect 1 bit of error. If 1 bit is flipped, your parity number doesn't match, right? You know that's something. And 2-dimensional parity bits is even more powerful. Right? So for example, if you have bits flipped, okay, here, you know which row and which column they don't match. And then you can flip it back. Okay, so this can detect, can fix, right, correct 1 bit of error. And you can also detect maybe, let's say, 2 bits of error, even though this row, you cannot see it because flip back, right? But these 2 columns you can detect, okay? And the 3 bits of error you can also detect, okay? Even though this column is flipped back, okay? But this column, you can detect it, okay? And 4 bits of error, then you cannot detect because all these 4 rows and columns are flipped twice. It flips back. And then is a concept of checksum. We may have a question answering kind of question, right? So ask you what is a checksum, okay? So if we have this kind of question, you need to tell us that checksum operates on 2 bytes, right? 16 bits. Basically, you have something like a 2 byte, 2 bytes, 2 bytes, 2 bytes, and you have those numbers, you sum them up, okay? And you will get the checksum and put it here, right? And then you need to usually we just do the data, by the way, okay? Not the endless settings, okay? And then you check whether after receiving the sum is also this number. If it's the same, then you're correct. If not, you are not correct. Okay. You need to mention the 16 bits and the summation, right? Those kind of things. Okay, over the frame data. Okay. Let me see. Okay, so that's the last slide I will cover today because we run out of time. We will finish in the next lecture. Okay, and the student asking question, will the exam be multiple choice? We will have multiple choice. That will be auto-graded. Beyond that, we will have TAs and me go through the answers. Okay, so there will be open answer questions, but will not be that open. Okay, so it's just not easy for auto marking. Okay. Yeah, so another question ask about the last slide. Basically, we will not take attendance, so if you don't have a question, you are free to leave. Okay. Here you're asking this question, right? So basically, for this, because I'm asking a student, his question is a direct message, not to everyone. Okay. So if you look at this number, this is 128 plus 64 plus 32, right? If you translate it to decimal, okay? So this will be your A, right? And how many bits you just count? We have here, this is 8 plus 2, it's 10. Okay, so I hope you answer a question. Clark, do you answer a question? So it's just a binary representation of the decimals. Okay. So we will have 18 questions. Another student asked how many questions. We will have 18 questions. Okay. So we will have one class, maybe 50 minutes. I think we can extend it to 60 minutes. Okay, but only 18 questions. A lot of them are multiple choice. So it should be enough time. Okay, more than enough. And for special accommodations, we will manually adjust the time. Right. So for the Clark's question, to me privately, I think it's yeah. So for interface 0, if you for the first, you can just write the binary format. Okay, the prefix this, right, and -10. Okay, something like this. But you know, if we are asking you to write in decimals, the third question you should use decimals, right, instead of binary strings. Okay. Yeah. So the first question you can just leave it binary. Okay. If you want to make it a decimal, it's fine, right? You just repeat the third question. So we will not get that mark if you merge them. Okay, that's fine. Right. The slide is already on canvas. Let me see. The student asking the question. The slide is here. So if you go to the dynamic syllabus, it's the midterm review. Okay, it's this slide. This one. Okay. Any other questions? Yeah. If you have questions, it's time to ask. Okay. Some questions are private to me, so not all students can see it. But you know, it's direct message to me. I also answer them. Any other questions? If not, we will go through, finish this review slide on Wednesday, and feel free to read it first on your own. Okay. There's a question. What do you mean by router 2? Ideal. Can you clarify a little bit? Okay, so yeah, feel free if you want to ask. You don't have to type. Okay, you can just unmute yourself and ask. Okay. Again, so that's the end of the class. If you have no question, feel free to leave. No worry. Okay. So you know, so for link 2, we start from here, right? So link 1, we start from here, right? So according to longest prefix matching, if you match this, also match this, right? So you will go to 1. Okay. So this is what we are telling you, right? So you can put 2 as a shorter prefix without worrying, hey, some of them go to 1. This is what we want to say. Is this clear?
Yes, yes, Professor.
Okay. Joshua, yeah. So one student asked whether the exam will be open note, right? It's officially not should not be open note. Okay, so otherwise it's too simple, right? So but again, so we only have so many time, right? So if you do open note, you will. If you search for every answer for every question, it will also take time. Okay, this is a timed exam. Try to prepare without open note. Okay, so even though maybe it's very difficult to check whether you are looking at the note, right? So because it's remote and we only see so many screen, right? So, but yeah, even if you open note, if you are not familiar with the content, you don't have enough time. Okay, so you should prepare the slides, you know, review slide carefully, right? To the extent you don't need an open. Any questions further?
Professor, just to further clarify your explanation before, okay. So on the link 2, use what I converted the what do you call the network portion of the IP address. It's pretty confusing when I compare with the host portion of the IP address.
Yeah, this is the network portion, right? But here it's unlike the others, very clear. You have 0, 0 to 1, 1, right? This whole segment from 0, 0, 0, some part of them doesn't belong to you, right? Do you understand what I mean?
Okay, I was under impression like, so when you say link 0, So the first line through to the second line, and on the link 1, it's from third line to the fourth line. On the link 2, is it supposed to be from fifth line to the sixth line, or? So
Well,
now you're saying
we don't have 6. We only have 4 ports.
I know, which I meant the destination address range. So you're saying the 0 link interface, we have the IP on the first line of the binary digit through the second digit, right?
Yeah.
So that was clear, which is the host part and the network part. So I got a little confused on the link 2, because when I converted the binary to the decimal, the first line shows me 224.665. Am I right?
4.65. What is 4.65?
I don't know. 224.65.
Okay. Exactly, but you can sum those 3 bits. Maybe it's 224. Yeah. But when you represent this number, you have a -x, right? So you tell you how many bits you look at. Okay.
Mm-hmm.
Right. So that basically tells you, hey, these are the second bytes. So, right.
Okay.
So what's your question? Is the question relevant to which part from 1 to 2 routes, or it's really converting bytes to decimals?
No, converting the bytes to decimal, bits to decimal, it was okay, but to figure out what is the network portion. For example, if I wanted to write on the link to what is the /x notation. For example, if it is it /16, or is it /24, or is it /10?
/10, yeah.
/10.
Yeah.
Okay.
So basically, we are saying that if you look at this segment, it's not totally from 000, starting from 000, right? So which means there's another range, which is from 000 to this 111 here. It's occupied 111. Okay, so you have here you have 16. Okay, this is the longest prefix. Okay, so this 10 will be shorter. So that's fine. You have 2 entries. The ones to those to 1 will be really go to 1, not go to 2. Okay, so that's what we want.
Okay.
Is this clear now?
Thank you. Yeah, it's pretty clear now. Yeah. Thank you, Professor.
Any other questions? Yeah, feel free to ask. Okay, so don't be shy, because this will be very close to the exam. Okay. And we will go through all these maybe 60 slides. Okay, so that's very important. Okay, so we narrow down significantly the range, and we, frankly speaking, there are way more than those slides what we covered so far. Okay, but we narrow down to help you guys prepare. Okay. Basically, we will test everything should be in this slide. Okay, this is a guarantee we can give you guys. If you prepare this slide well, you don't have to go to the original so many slides. Okay. Okay, it seems that I cannot see any new questions, so that we will go through stuff next time. Okay, so there's one student asked about math questions. Yeah, we have a math question. Okay, so we have some slide on math. Okay, so let me see which part is it. Right, so we have some in the review slide. We have some formulas go through this. Okay, how to calculate stuff. Okay, so but we will review next time. Okay, like this could be a question. Okay, right, so but we will go through this next time. You can also look at the slide first. Okay, then if you have questions next class, you can ask for them. Okay, so that's the end of this class. I will see you guys on Wednesday. Thank you. Have a nice day.